welcome. In this video, we're going to do some last-minute practice for the Cal BC exam. And what I've got for you is a set of 60 multiple-choice questions that kind of go through all the topics from the definition of a limit all the way to Lagrange error bound. And if you were just reviewing for Calculus AB only, well, that would just be the first 38 questions in this problem set. All right, now the first one asks, which of the following graphs has the property where the limit is x approaches 4 of f of x exists? Okay, remember that the definition of the limit is that we need to be approaching the same y value as we approach x equals 4 from both sides. Like here, yeah, right? From both sides, I'm approaching that empty circle. Over here, same thing, okay? The limit as x approaches 4 exists because I'm going to the same point. Over here, I'm approaching what looks like 4 up here, but only 2 down here, and since those aren't the same thing, I'm going to say that the limit as x approaches 4 of f on number 3, that fails to exist, so it's going to be 1 and 2 only. So I'll read this one. All right, now we're going to talk about some limits with infinity. Okay. And this is the type of thing, well, okay, well, I'm seeing it's degree 2 on top and degree 2 on bottom, so I know that I would be dividing the ratio of the leading coefficients. But this is kind of factored. So what I would need to do is I would need to think about what would happen if I, say distributed the 2x times negative x. That would be negative 2x squared, plus some other stuff. Because we know that all that matters is going to be the coefficients of x squared in the numerator and the denominator. And then in the denominator, I'm going to have, x squared. Yeah, I can do that. That's going to be plus 2x minus 3. And so I know that the ratio of the leading coefficients is going to be negative 2 over 1. And so that would be that limit. All right. Continuity. Definition of continuity is that it's going to be continuous if the limit of the function is equal to the value of the function at that particular point. So what we need is we need the limit of f as x approaches 2 to be equal to the value of f at x equals 2, which they're telling us is k. Okay, the limit of f as x approaches 2 is going to be, well, I guess whatever I would get, canceled those things off. And so that would be, I would need 2 times x equals 2 plus 1. Right, I'm taking this 2 and plugging it in for 2x plus 1. And I would need to set that equal to k. Okay, and that would be 5. Oh, okay, that's pretty straightforward. All right, now we're going to move on to the idea of differentiability. Remember that something is differentiable provided that, its derivative exists. And that's going to mean that we aren't sitting at a sharp corner, at a vertical tangent, or a discontinuity. Okay, so what I'm going to need to do, first I'm going to check to see if it's continuous. Okay, in order to check if it's continuous, I'm going to check is the piece from the left the same as the piece from the right at the kind of x value that they're sharing. Okay, so is x squared equal to 6x minus 9 where x equals 3? Okay, so I've got 9 equals 18 minus 9. Yes, okay, so it is continuous. As for differentiable, I'm going to have to check the two pieces of derivative. Okay, so I'm going to say f prime is going to be 2x and 6, okay, when x is less than 3 and when x is greater than or equal to 3. Okay? And so I can see, all right, when I plug in x equals 3 to the derivative, I'm getting the same slope from both sides, which means that it's going to be, it's going to pass off from y equals x squared to y equals 6x minus 9 smoothly. Okay, so that means it'll be continuous and differentiable. And so I'll say both continuous and differentiable. This one is a definition of the derivative question. Okay, so you need to remember that f prime of x is the limit as run goes to 0 of rise over run. Okay, so this looks like it's asking me for the derivative of cosine x with x equals 3 pi over 2 plugged in. Okay, well, I can do it that way, and I could say, all right, well, this is negative sine of 3 pi over 2, because we know that the derivative of cosine is negative sine. And sine of 3 pi over 2 is negative 1, so negative 1 would be positive 1. Okay, that's one approach. But I've got another approach for you. Maybe you aren't recognizing that, or you don't just think, oh, hey, that's a disguised version of a derivative question, and you see a limit that's going to go 0 over 0, and you're thinking, I want to use L'Hopital's rule. Okay, well, you see that this is going towards 0 divided by 0. If you just plug in h equals 0, I'm taking cosine of 3 pi over 2 minus cosine of 3 pi over 2, dividing by 0. So I'm going to use L'Hopital's rule, and I'm going to say that this is equal to the limit as h approaches 0, and I'm going to take the derivative of the top and of the bottom with respect to that variable h. So cosine of 3 pi over 2 plus h, if I take the derivative of that, I'm going to get negative sine of 3 pi over 2 plus h. Okay, cosine of 3 pi over 2, that's a number. The derivative of that number with respect to h is going to be 0. And then the derivative of h with respect to h is going to be 1. Okay. Approaches 0, I am taking, again, negative sine of 3 pi over 2. Okay. So either way, I'm going to get negative 1. Okay. Now, asymptotes. Okay, I think what I want you to remember about asymptotes is that a vertical asymptote is caused by division by 0. Okay, specifically like some non-zero number divided by 0. And a horizontal asymptote, you're thinking the limit as x approaches infinity. Okay? So if y equals 2 is the horizontal asymptote, then I know that the limit of, ax plus b as x goes to infinity divided by x plus c, well, that's going to come back, okay, first degree on top, first degree on bottom. That's going to be, same power, divide the coefficients. That's a divided by 1. But they also told me the horizontal asymptote was y equals 2. Okay, so I know that a equals 2. Okay, vertical asymptote at x equals negative 3 means that, okay, like that over here, I know that means that x plus c needs to equal 0 when x is negative 3. Okay. And then, so negative 3 plus c equals 0, that's telling me c is going to be 3. So if, wait, yeah, I'm not really sure what b was going to do for us, but they didn't ask us about b, so yeah, I guess that was just there to distract you. A plus c is going to be 2 plus 3, and that's going to be 5. All right, average rate of change. We know that average rate of change is f of b minus f of a divided by b minus a. Okay. So on the closed interval 0 to 3, it's going to be f of 3. So 3 to the 4 is 81. Minus 5 times 3 is 15. Okay, f of b minus f of a will be 0 when I plug in 0 for x to the 4 minus 5x divided by 3 minus 0. Okay. 81 minus 10 would be 71, and 71 minus 5 would be 66. So I'm taking 66 divided by 3, and that's going to be 22. Oh. Okay, this one's really, I didn't want to just ask you a direct power rule question. I didn't think that would be too easy for the level you're at right now, but I might ask you one that, merged the power rule and something else. And so it's saying, find the point of inflection and then write the equation of the tangent line at the point of inflection. Okay, so point of inflection, sign change in y double prime. Not a 0 of y double prime. Okay, oftentimes these do happen at places where y double prime is equal to 0, okay, but it's not a 0 of y double prime. It's a sign change of y double prime. It's a point of inflection. Right, so y prime will equal 3x squared plus 6x. Y double prime will equal 6x plus 6. And if I think about the graph of that, it's going to change signs at x equals negative 1, right? Because it's going to go from negative to positive. Okay, this is the graph of f double prime. Okay, so I know that the x I'm interested in is negative 1. Okay, yes, f double prime was 0 there, but that's not my reason for it being a point of inflection. It's because the graph crossed the x-axis. Okay, so now I've got an x value. I'm going to need a y value, but luckily I've got a formula for that. Negative 1 to the 3 is negative 1, plus 3 times negative 1 squared plus 2. So it'll be 4. And then I'll need a slope, but it won't be too hard to find because, let's see, y prime at x equals -1 is 3 times -1 squared plus 6 times -1. That'll be a slope of -3. Oh, I didn't even need to get the y-coordinate because there's all different slopes, okay? If you noticed that while you were looking at the answer choices, you could have, gone without that computation of y because, you could just determine based on the slope. All right, product rule. We've got this. We know how to do the product rule. We're going to take the derivative of one of the factors while leaving the other one the same. Then we'll take the derivative of the other one while leaving the first one the same. Okay, and we know that the derivative of e to the x with respect to x is e to the x. Okay, it looks like they've done a little factoring, but I think we're going to be able to deal with that, right? We're going to factor out an e to the x and an x from both of these, and I'm just left with a 2 over here and one extra copy of x there. So that would be answer choice C. Do a product rule question, you should also do a quotient rule question, right? We know that the derivative of top over bottom is going to be bottom times the derivative of the top, right? The derivative of log x is 1 over x, minus the top times the derivative of the bottom, divided by the bottom squared. Okay? So that's 1 minus log x divided by x squared. Okay? They're always going to give you that option that's off by a factor of -1 because so many people misremember the quotient rule. I need you to remember that properly, okay? I saw a number of people that were, had it backwards on the most recent free response, and yeah, you need to have that right, if we're going to go in and take the exam. And the chain rule is another one that, hopefully by this point in the course, it's been deeply ingrained into you. And so I didn't want to just, have one that was easy, so I figured I'd do a second derivative problem on this one. So we'll go over here and we'll say, all right, well, the first derivative is dy dx. And we know that the derivative of cosine is negative sine. So it would be -2 sine of x divided by 2. But then I would need to multiply by 1/2 for the chain rule, right? Because the derivative of x divided by 2 with respect to x is 1/2. So I'm going to divide by 2, and then I'll just have negative sine of x over 2. And then the second derivative, I'm just going to take the derivative again, and that's going to be equal to, okay, the derivative of negative sine would be negative cosine, but I know the same thing's going to happen here. I'm going to have to multiply by 1/2 for the chain rule. So I've got -1/2 of cosine of x divided by 2. There it is right there. Move on. Okay, the derivative of f inverse. This is kind of an obscure topic, but it's one that I've kind of reminded you of in class recently, so I think that you should be able to do this. Okay, the formula that you need to know is that f inverse prime is 1 over f prime of f inverse, and you want to remember that f inverse is just some x value. Okay, well, if g is the inverse function of f, then g prime of 3 is f inverse prime. So that's going to be 1 over f prime of f inverse of 3. Okay, and if I need to know what is f inverse of 3, I'm going to set f of x equal to 3 and solve for x. Okay, well, oh, hey, look, I found where f of x equals 3. That's x equals 6. Okay, it's going to be 1 over f prime of 6. They're going to tell me that that's -2, so then I'd be 1 over -2. Okay. This next one's going to require the use of a calculator, and I've added a few on this problem set that require a calculator, but not a whole lot. Okay. So the function f has derivative given there. On what intervals is f increasing? Okay, well, you hear increasing, you want to think, oh, okay, increasing is where f prime is greater than 0. So I'm going to, just use the calculator to produce a sketch of f prime. Okay, that's not it. But I can type it in, sine of x to the 3 minus x. Make sure I'm in radian mode. And I'm gonna set the window to 0 to 2. -1 to 1, sure. Yeah, okay. So it's going to be positive on 0 to 2 between these two x values. So I'm just going to hopefully be able to just compute one of the zeros and find my answer choice. Okay, that's x equals 1. Okay, I could have definitely seen that coming, okay, because the sign of 0 is 0. So I guess I'm going to need to find, yeah, there's a difference between A and B. So I bet it's going to be B because I bet this is up here. That's 1.445. Remember, I don't know, if you've been in my class, you've been with me a whole year and you've never seen me use calculate 3 or calculate 4. That's just not ever the thing to do in AP Calculus. I just wanted to point that out. I bet it's between 1.5 and 2. Yeah, sure. And then that's 1.690, 5, 6. Okay, so that's going to be answer choice B. All right, local extrema. Remember that f of x has a maximum when f prime goes from positive to negative because f went from increasing to decreasing. So I know that I'm looking at, okay, the derivative goes from negative to positive. This is going to be a minimum. And I could say the same thing about this one because the derivative went from negative to positive. And then this one's going to be a maximum because the derivative went from positive. Okay, just think about what the derivative sign does to the original. Okay, so I'm seeing 2 minima and 1 maximum, so that's going to be answer choice A. All right, here's one about it's kind of about both the intermediate and the mean value theorems because one of the wrong answer choices has to do with that one. So, but I kind of forget which one it is. Okay, so which of the following statements must be true? F is increasing between -1 and 5. Okay, they didn't say that, f prime is a strictly decreasing function, or that, f prime is always positive. They didn't say that. It just looks like f is always increasing. But it could be that between 4 and 5, f prime went negative briefly. It went 5 to -1, back up to 2 or something. We don't know what's happening, so we can't say that it must be increasing. I don't think we can say that the graph of f must be concave down from -1 to 5, although it appears that it is, right? F prime looks like it's decreasing. We would need to know f prime was decreasing the whole time between -1 and 5, not just, at these points that we can see. Okay, so I'd probably B is true, but we don't know that, and it's not must be true. Okay, there exists a C between -1 and 5 such that f prime of C equals -3/2. No, that would be if we saw this was, I don't know, -2 or something, then I'd know, oh, okay, f prime is continuous because f is twice differentiable, and we know that if f prime is differentiable, then f prime is continuous, okay, but we don't really have any evidence to say that f prime is going negative. So it's going to be D. Okay. And D is using the mean value theorem. If f is twice differentiable, then that means f prime is differentiable. And that means that there's going to be some place between -1 and 5 such that the derivative of f prime, which is f double prime, is equal to the average rate of change of f prime over the interval -1 to 5. So that would be f prime of 5. No, that's not 5. F prime of 5 minus f prime of -1 divided by 5 minus -1. That's going to be -9/6. And that's -3/2. So that must be true, right? If f prime is differentiable, then there must be a place where the average rate of change is equal to the instantaneous rate of change. That's the mean value theorem. All right, here's another product rule question. But this time I'm asking you about the concavity. So let f be the function given by f equals 2x e to the x. And we want to know when f is concave down. So if we want to talk about concavity, we need a second derivative. So I'm going to start with f prime using the product rule. I'm going to take the derivative of 2x and leave e to the x the same. Then I'm going to leave 2x the same and take the derivative of e to the x. Okay. And I think that to make my life a little easier on the next step, I'm going to factor out the 2e to the x's. Okay, and then I'll be left with a 1 plus x. Because now I can do the product rule again on this, and it will be a little better than trying to keep track of all that stuff and then factoring it, I think. Who knows? Maybe it'll be the same function. I don't know if it'll look the same. All right, so I'm going to take the derivative of 2e to the x, because that's pretty easy, and I'm going to leave 1 plus x the same. Then I will leave 2e to the x the same, and I'll take the derivative of 1 plus x. And then, yeah, so it'll be 2e to the x times 1 plus x plus another 1, well, that would be x plus a total of 2. Okay, that's f double prime. Okay, now I need to figure out, where this thing is positive and negative, and this 2e to the x times x plus 2, I don't know what the graph of that looks like. So I'm going to make a sign chart. I'm going to think about all the places where f double prime is equal to 0. Well, 2 is never equal to 0. Neither is e to the x, so the only place where f double prime is going to be 0 is going to come from where that thing in the brackets is 0, and that will be when x is negative 2. Okay, so now, just from that, I know that I've got it down to 2 answer choices, okay, which we know is really helpful to us. If we can get all of our answers down to 2 and just randomly guess for multiple choice, we'll be on pace to get a recommended score. Okay? I don't recommend you do that, right? I want you to know the answer to all of them, but if we can eliminate answer choices, we're giving ourselves a much better chance of guessing right. Okay. So, oh yeah, test something to the left of negative 2, like, I don't know, negative 4. Okay, f double prime of negative 4 equals 2 times e to the negative 4, though that's a positive number, multiplied by negative 2, that's a negative number. And then on the other side, I've got f double prime of 0 would probably be a good number to plug in. That would be 2e to the 0, also a positive number, times 0 plus 2, and that's positive. Okay, so I know that it's concave down on those x values, so that's where x is less than negative 2. Okay, on the topic of curve sketching, I added 2 problems. I'm really not entirely sure why I did that, but maybe I'll look and it'll make sense when I look at the second one. Okay, so up here we've got f, and we want to know which could be the derivative. Okay, now when you're thinking about the derivative graph, you really want to think about 0 slopes, positive slopes, and negative slopes. Okay. This is looking pretty close to 0 also. It looks like it starts off pretty flat, it ends flat, but it's positive, then 0, and then negative, and goes back to 0. I think that that's it. That's what I'm describing, right? Starts off pretty close to 0, increases for a while, hits a 0. Yeah. So it's the f prime is positive throughout, then it hits 0 right there, and then it's negative after, and it goes back towards here. Yeah, I'm convinced. Oh, I see. Yeah, this one. I don't know if this is really curve sketching, but just, what does it mean for a function's derivative to be negative? Okay, so f prime negative means I'm looking for something that's decreasing. F double prime being negative means I'm looking for something that's concave down. And f being negative, well, I know that means that the graph needs to be beneath the x-axis, but that's true for all 4 of these. I think there was a 5th answer choice originally on this problem, and I removed it because it was above the x-axis, and I just didn't think that anyone was going to get fooled by that. Okay, so decreasing and concave down, that's going to be this one. This one's concave down, but over here it's increasing, so that's just not going to have a negative slope at all times. Okay, this one is decreasing always, but it's kind of like smiling. Oh, whoops, I put the wrong eyes. Put the happy eyes there. It's smiling over here, but we said it needed to be concave down. All right, and we need to be able to find absolute extrema using the closed interval test, the candidates test. And this did not print. I found on AP Classroom that v of t didn't look right. The exponents kind of got cut off. And so then I tried to make it, and I thought it filled out the space a little better, but it just looks terrible. So I'm going to just copy down the equation for v. I can tell that that's t to the 3 minus 3t to the 2, 12t, and 4. Okay. We want the maximum acceleration on the closed interval. That means we got to do the candidates test. Okay, so the acceleration is the derivative of velocity, which is 3t squared minus 6t plus 12. So I want to know the maximum possible value of that on the closed interval 0 to 3. So I need to be considering the value of the acceleration at the endpoints and at the critical points of A. And this is pretty much the only time I know when we would be interested in taking the derivative of acceleration would be to find the maximum. Okay, but I'll just plug in A of 0, that's going to be 12. A of 3 is going to be 3 times 9 is 27 minus 18 plus 12. Okay, so that's definitely bigger than 12. And then I need to know where is a prime of t equal to 0. Well, a prime of t is 6t minus 6. A prime equals 0 when t equals 1. Okay, so I'm going to check the value of a when t is equal to 1. I mean, within reason, you probably know that this is a relative minimum because the graph of a is an upward-facing parabola. But, you know, in the free response, I've told you many times this year, you got to check all the endpoints to just make sure you're going to get the justification point. Okay, so I'm checking all of my endpoints and critical points. And a of 1 is going to be 3 minus 6 plus 12, which is definitely less than 12. Okay. So this is kind of like my winning value. So this is 12 plus the 9 that I just, broke off with parentheses, and that's going to be 21. And we need to be able to take derivatives implicitly. So if x to the 3 minus 2xy plus 3y squared equals 7, then just find dy dx. Okay, this is a pretty typical problem because, or it's a typical College Board question because it's got x times y in it. It seems like almost every one of these implicit differentiation problems that comes from the College Board has an x times y. So you need to make sure you're able to do that. Okay, we know how to take the derivative of both sides of this equation. We're going to start, we're taking with respect to x, so the derivative of x to the 3 is 3 times x squared. Okay, now on this, I'm going to look at it as a product of negative 2x and 1y. I think that's the way to go. So first, maybe I will take the derivative of negative 2x, and I'll leave y the same. And then I'll leave negative 2x the same and take the derivative of y. Okay. Now I need to get rid of those because, okay, yeah, that is a plus 3y squared. Okay, so the derivative of 3y squared is going to be 6y to the first, but I'm taking the derivative with respect to x, right? So really this is like a function of x, it's y of x. So it would be 6 times y of x to the first power times the derivative of y with respect to x for the chain rule. And then the derivative of 7 with respect to any variable is going to be 0. So at this point, what I want to do is I want to get rid of anything that doesn't have dy dx. So that would be adding the 2y and subtracting the 3x squared, and factoring out the dy dx from what I've got over here. Oops. Dy dx times 6y minus 2x. That's going to be equal to 2y minus 3x squared. Okay, and so then dy dx will be equal to 2y minus 3x squared divided by 6y minus 2x. You're like, oh man, it doesn't match up quite. Looks like B. Is it the same? And it is the same, right? Because what they've done is they've multiplied the top and the bottom by -1. Probably they maybe pushed everything with dy dx over the right side of the equation and solved. Then you would get exactly what you had in B. But it's the same answer, so we're going to choose that. Okay, linear approximation. It's been a while since we've talked about this, but we've been doing it all along, right? We did it in the first semester when we were studying all the AB topics, but then, more recently, Euler's method. Okay, well, linear approximation is Euler's method with one step. Okay, a first-degree Taylor polynomial, that's a tangent line. Okay, so we've been using these things, we've just been using other names for them. So I might go over here and say, all right, we've got local linear approximation. Okay, that's something. We need to use the tangent line. It's interesting that they didn't actually just use the word tangent line. But maybe that was part of the difficulty. The problem is that you need to know that local linear approximation means use the tangent line. Okay, so I've got a point. That point is 5 and 3. I've got a slope. Slope is going to be f prime of 5 equals 4. So I can write my equation as y minus 3 is 4 times x minus 5. And then my approximation, approximation has two p's. That's going to be y is approximately equal to 3 plus 4 times, well, they want 4.8 plugged in for x. Okay, so that would be 3 plus 4 times negative 0.2. So I've got 3, I'm going to subtract 0.8, and I'm going to get 2.2 left. All right, related rates. Now, I kind of went back and forth on this. I decided to just do one of everything, right? Pretty much. And so I could have put in, one with a cone or one with a sphere or whatever, but I just decided to do this one. I didn't really have a good reason to choose this one. But if you need more and you're looking at the original document, which I definitely have linked in the description of the video, you can click that hyperlink where it says related rates 43-44. And that'll take you to the Google Doc for this. That would take you to the video of the lesson, the homework problems, the extra practice problems. I put out a lot of extra practice problems for related rates. So if you need those, go click right there. And, well, I guess you can't click right there, but on the original document, click on the link and see what you can find. See what you can work on your own. Okay, but I'll jump in and do it now. So the sides of the rectangle increase in such a way that dz dt is 1 and dx dt is 3 times dy dt. All right, well, the only thing I know about x, y, and z is going to be that x squared plus y squared equals z squared. And it seems like pretty much all of the ones that have a right triangle, except for the shadow or cone ones, those deal with a proportionality relationship. But these ones that have a triangle, it's very, very often just starting with the Pythagorean theorem. The ladder problem, that's also Pythagorean theorem, but that's a different discussion. We're not doing the ladder problem. We're going to take the derivative of both sides of this equation with respect to time. So it's 2x, but x is a function of time, so I have to multiply by its derivative for the chain rule. 2y dy dt. Those are going to add together and make 2z dz dt. Okay. Now, I'm going to say, oh, wait, they said dz dt is 1. And dx dt is 3 times dy dt. We want to eventually find the value of dx dt, but I guess we're going to need to find, the value of dy dt first to make that happen. But we'll just multiply that dy dt by 3 to get dx dt. So it shouldn't be too bad. All right, when x is 4 and y is 3, that means that z is going to be 5. So I've got 6 times 3 is 18 dy dt, which I might just abbreviate with y prime for now, plus 2y would be 6 dy dt, because y was 3. And that's going to be equal to 2z times 1, and that's going to be 10. So that's 24y prime equals 10. And that means y prime equals 10 divided by 24. I am not seeing, this is not going to work out for me. I'll just keep going for a second. X prime is 3 times y prime, which is, hold on, I'm going to have to figure out what I've done here. Okay, I found what it was. X was 4, so that would be 4 times 3 is, no, 2 times 4 is 8, times 3 is 24. Goodness, I almost made another arithmetic error. So yeah, okay, that makes a lot more sense. So 30y prime is equal to 10. Y prime is 10 divided by 30, meaning x prime is 3y prime. That'll be 30 divided by 30, and that's 1. Okay, pardon me. Hate those arithmetic errors. All right, now slope fields. Okay, the slope field, one thing I told you about slope field is to kind of scan side to side and up and down to try to determine if the formula for dy dx depends on x or depends on y or depends on both. Well, as I move side to side, I'm seeing rows that all have the same slope. Okay, and so that means that I'm pretty sure that this equation needs to be independent of x. But then when I go vertically, I'm seeing a wide range of slopes. So I know this has to depend on y. Okay, so I got these out. They're down to 2. Now the other thing that I think I'm supposed to see is that y prime is equal to 0. Slope is 0 when y equals 2 and when y equals -2. Okay, so that's why it's going to be b. Okay? Because for a, when y is -2, the slope would be also negative 2. And we're seeing a horizontal slope through here. So that's why I know it's asymptotic. Ooh, antiderivatives. Now, we've been computing antiderivatives on a daily basis since about October, so I don't think I need to ask you a whole lot of those, and a lot of the things we're going to do moving forward after this point are going to require the use of an antiderivative. So I figured I would remind you of some obscure antiderivatives that you might need to know. And secant squared, I need to know, hey, that's the derivative of something, right? That's the antiderivative question. What is this the derivative of? So secant squared x is the derivative of tangent x with respect to x. So I know that the antiderivative of secant squared x with respect to x will be tangent x plus c. Okay. Now, separation of variables is a thing that, at least this year, we were really good at when we were doing it in the unit, and then I went to give y'all some practice tests, and it was like y'all had forgotten all the work that you'd done the whole time. So let's just go ahead and start from scratch on this one. And it'd probably be all right if it was a little bigger. So I'm going to say I need to separate variables, so I'm going to multiply both sides by y and multiply both sides by dx. Okay. Then I'll anti-differentiate both sides. Okay, so antiderivative of x to the 2 with respect to x is 1/3 x to the 3rd. And a plus c. And that's going to equal 1/2 y squared. Okay. Now I'm going to start solving at y, so I'll be multiplying both sides by 2. Remember, I don't really need to multiply c by 2 because it's going to become some other constant. Okay, wait, but that's y squared. And then when I go to solve for y, I'll need to take the square root of the whole right side, right? I can double c, and that'll just become a new constant. But taking the square root of 2x, or 2/3 x to the 3rd plus c, that's not the same as taking the square root of 2/3 x to the 3rd and then just adding some other constant. That would not be the same. So if I'm taking the square root of both sides of an equation, that's going to incur a plus or minus. And so I'll have a 2/3 x to the 3rd plus c in here. And maybe, oh, okay, well, now I've got it down to, I guess maybe c was 0, right? I could allow for that possibility. But if you see y of 3 is negative 2, well, if you plug in 3 here and you take the positive square root and answer choice D, you're going to get a positive number. And same for c, so that's why I know it's got to be e. And that usually happens on multiple choice problems for separation of variables. There's usually places along the way where you can just eliminate answer choices and kind of just keep going until you only have one left standing. Okay, in free response, we got to be very careful to show all of our work, make sure we're not making algebra errors because these are worth a lot of points in the free response. But in multiple choice, there's, steps we can take to make it go a little quicker. All right, L'Hopital's rule. We've already done this once in this video in kind of a different context. We'll do this one for real. Okay, we're going to, anytime we're confronted with a limit, we're going to try to just plug it in. Because every once in a while, it'll just, 0 or won't be infinity or infinity. It'll just be two numbers divided by each other, and we can just plug in and move on with our lives. So I'm going to try, it's going to be e to the 0 is 1 minus cosine of 0 minus 2 zeros divided by x squared minus 2x. Well, that's 0 over 0. I'm going to need to use L'Hopital's rule. And while I'm writing that, I'm going to remind you to not ever write equals 0 over 0, because 0 over 0 is not a real number. Okay? And that can lose you the justification point on the free response. Multiple choice, nobody's scanning through your booklet to make sure you didn't write 0 over 0 or abuse infinity notation or anything like that. But in free response, that type of thing can cost you. So I don't want that to happen to us. So we're going to show it goes to 0 over 0. We're going to say that we're going to use L'Hopital's rule. And we're going to maintain our limit notation. In multiple choice, I guess you do whatever you want. But I'm going to display my work as if it was a free response situation. And that'll be e to the x plus sine x, right? Because the derivative of negative cosine x would be negative sine x. And minus 2, oh yeah, that's going to come back. Okay, divided by 2x minus 2. Oh, okay, for some reason I thought this one was going to come back and need a second iteration, but it's not, right? Because as x goes to 0, I'm going towards e to the 0, which is 1. plus sine of 0, which is 0 minus 2, divided by 2 zeros, well, that's 0 minus 2. So I've got negative 1 divided by negative 2 is going to be positive 1/2, like that one. All right. Now the Riemann sum, this isn't really a question about computing the Riemann sum or getting an approximate value of an integral. I'm just going to tell you, if you need more practice on Riemann sums, I put out a whole worksheet of Riemann sum examples from various free response situations. You can go do that, right? This is about the, kind of the theory of the Riemann sum. Is it an overestimate or an underestimate? Okay? So I will say I'm going to use some different colors for left Riemann sum, right Riemann sum, and trapezoid sum. So left Riemann sum will be, and what I've found is that it's easiest to determine whether it's an underestimate or an overestimate if you use just a low number of subintervals. So I'm just going to use 2. And I'm going to use the left edge of my subinterval to give my height of my rectangle, and the left edge of my subinterval to give me my height of my rectangle. And I'm going to see that left is an underestimate. Okay. And then for the right Riemann sum, well, that's where I'm going to split it in half, the same way I did before, and I'm going to use the right edge to represent the height of my rectangle. Okay, I'm taking a little bit of liberty, but you can see that right is going to be an overestimate. And it's going to be an overestimate by quite a bit, because I think that might end up being, yeah, that is going to matter. Okay. So for the trapezoid sum, I'm going to say, all right, the worst possible trapezoid sum is that, right? And although it is counting this area here that the blue right Riemann sum was not, there are these huge areas out here that the right Riemann sum is counting that the trapezoid sum is not counting. So while the trapezoid sum is an overestimate, it's not going to be as much of an overestimate as the right Riemann sum. So I'm going to choose answer choice A, right? Because L is the left Riemann sum. It's less than the true value of the integral. The true value of the integral is less than the trapezoidal sum because the trapezoid overestimates, but not by nearly as much as the right Riemann sum does. Okay, now the fundamental theorem of calculus, again, I don't think I need you to practice a whole bunch of really easy integrals, but I'd show you this one and remind you of some advice I've given you about integrating quotients before. Okay, if you see a fraction in the integrand, you've got to do something. You can't just do nothing. We don't have a quotient rule for anti-differentiation. You certainly can't just anti-differentiate the top and anti-differentiate the bottom separately. We've never done that in this class. It's never the thing to do. We got to do something like algebraically first, and we'll see some more examples of that once we get into the C topics. But what I'm going to do is I'm going to say, all right, well, x minus 1 divided by x, really what that is 1 over x multiplied by x minus 1. So that's going to be 1 minus 1 over x. Okay? So if I'm integrating from 1 to e to the 2 of 1 minus 1 over x dx, I'm going to find an antiderivative. I'm going to say that's going to be x minus the log of the absolute value of x. I'm going to plug in 1 in e to the 2, and I'm going to subtract. Okay, so this is going to be e to the 2 minus the log of e to the 2. Now I know that the log of e to the 2 is 2 because that's the special exponent I put on e to get e to the 2, which is pretty clearly 2. And then when I plug in 1, I'm going to have 1 minus the log of 1, and I think about what exponent do I put on e to get 1, that would be the 0 exponent. And so I've got e to the 2 minus 3, and there it is right there. Okay. Average value is something that I think I almost didn't put on this problem set, but I remember just at the last second, and I didn't want to go and renumber all the problems and have it go to 61, so I just kind of threw it in with this one. We need to know the average value. We can compute it by running the integral, in this case from 0 to 8 of f of x dx, and then dividing by 8 minus 0. Okay, so this is going to involve, some geometry. And that was another thing that I felt like was kind of lacking on this problem set was geometry integrals. So we're going to do that. Okay, this has a height of 1 and a width of 8, so it's going to be 8 units. This triangle will have a width of 4 and a height of 2. So its area will be half of 8, which would be 4. And that, okay, I believe it. Yeah, okay, I see it. And then this semicircle would be half of a circle with radius 2, so that's 1/2 pi times 2 squared. So half of 4 pi is 2 pi. So the integral is 2 pi plus 8 plus 4. And then I need to divide by 8 because I'm taking the average value. So that's going to be pi over 4 plus 12 divided by 8 is 3 divided by 2. What's going on here? Oh, yeah. That's going to be pi plus 6 divided by 4. I just couldn't see that. All right, yeah, that's average value. Okay, change of variables, U-substitution. Okay, I chose this one because, you know, this is the type y'all would have a tough time recognizing it's supposed to be U du. Okay, but anytime you have a log x and an x and an integral, it's going to have to be U du because we don't anti-differentiate log of x in AP Calculus. Or if we do, it's as a C topic, and we need to know that we do integration by parts on that. But even that, I think, is a bit of a stretch at this point. Okay, so if you see log of x and x in the same integrand, well, that's got to be a hint that something's a derivative of something else, which is that U du pattern. So I'm going to let u equal log x because that's pretty much always the way it goes when there's a log x and an x and, you know, an integral that you use U-substitution for. So u is going to be log x. Du is going to be 1 over x dx. And maybe I could, you know, convince you of what I'm going to be doing by, you know, instead of dx over x log x, I'm going to write this as 1 over log x times 1 over x dx, right? And look, 1 over x dx, that's du. So this is going to be like a perfect match. Now I just need to convert my bounds. So when x equals e, u equals the log of x. So the log of e is the exponent I put on e to get e, and that would be 1. And then when x equals e, u is going to be the log of, wait, e to the 2. U is the log of e to the 2. It's the exponent I put on e to get e to the 2, and well, that's 2. And then what else? Oh, yeah, so I'm going to actually, you know, kind of convert this to a u integral. This is the integral from 1 to 2 of 1 over u du. And now it's much easier, right, because I can anti-differentiate 1 over u. Log of u, and then I'll let u run from 1 up to 2, and that's going to be the natural log of 2 minus the natural log of 1, which is the natural log of 2. Ooh, that was kind of a mean answer choice there. But you need to know that the log of 1 is 0. It's the special exponent you put on e to get 0. I've said it already a few times in this video. I've said it a bunch of times this year, and hopefully you've internalized it. Right, now this motion problem is going to require the use of a calculator. Okay? And it's going to require you to remember the formula for total distance traveled by a particle that moves along a straight line. Okay, that's from back in the first semester, but that can show up in Cal BC. Right? They can ask you one-dimensional motion questions. Oh, whoops, pardon me, I'm just trying to get back to the main screen there. Okay, we need to know that the total distance is what we get by integrating speed. Just like in the parametric, the 2D case. Okay, we're going to be integrating from one time to another on speed, but on a line, speed is just the absolute value of velocity. So what I'm going to do is I'm going to take the absolute value of log of t plus 1 minus 2t plus 1, and I'm going to integrate that with respect to t. Oh, you can't see that. Maybe I'll just kind of shrink that down a little bit. Yep. And I'm going to be integrating using Math 9. Okay, I'm going to grab the absolute value from F2. I learned about that this year. That was a new development for me. Oh, no, but I put the absolute value. Oh, goodness. All right. Integral from 0 to 2 of the absolute value inside the integrand of log of t plus 1, we use x, right? It's going to come back the exact same. Go on the outside of the absolute value. No, don't go on the absolute outside. I'm going to subtract 2t and add 1. Respect to x. Let it think. 1.540. There it is. Ready to move on. All right, the definition of the definite integral. Okay, this one's always tricky. People are, prone to getting intimidated by it, but there's a couple of tricks that we can use to make our life much easier. First, looking at the width of the interval we're integrating on. Okay, this goes from 2 to 6, so it has a width of 4, so I know that delta x equals 4 divided by n, where n is the number of subintervals. Okay, meaning this one and that one are both out. Okay, also, we're going to think, okay, what is these x's? X is what I'm putting into the square root right there. Well, x needs to start at 2 and go up to 6. And so this is one that's starting at 2 and going up to 6, right? And because as n approaches infinity, no, I don't even want to get into the index. You can see that this one starts at 2 and goes up to 6 because of that 4. Whereas this one would start at 0 and go up to 4, this guy right here. So I'm going to say that's answer choice C. Okay, we'll get rid of the calculator. I don't need that anymore. Or not, at least not for this problem. Okay, y equals 5 plus the integral from 2 to 2x of e to the negative t squared. Which of these is true? Okay, I think I'm going to start out with the derivative, right? That's why I put this problem on here, was because of the second fundamental theorem. It looks like I'm really zoomed out. That's all right, though. dy dx is going to be where I'm going to take the upper bound and I'm going to throw it in wherever I see t in the integrand. So e to the negative 2x squared. And then I need to remember to multiply by the derivative of that 2x for the chain rule, right? This derivative right there. Okay, that's one that a lot of people will forget about. So I would simplify this and say this is e to the negative 4x squared multiplied by 2. And okay, so that gets me down to answer choices D and E. Okay, y of 0, well, y of 0 would be the integral from 2 to 0 of e to the negative t squared, which is not going to be something you're going to be able to compute by hand. But it's probably not going to be 5, right? Because that would be if the integral was 0, and I know that e to the negative t squared is a positive function. So it's got to have a positive amount of area, so it would actually need to be less than 5. Y of 1 is going to be 5 because when I plug in 1 here, I'm going to be integrating from 2 to 2, and we know that's 0. So it would be 5 plus 0. And so I'm going to choose answer choice E. Okay. This next one is using the formula that I like to kind of go back to a lot in my AP calculus class. It's f of b equals f of a plus the integral from a to b of f prime of x dx, right? That's how we get our ending value by going with our starting value and adding in some sort of accumulation of a rate of change. Okay, it makes a lot of sense. So if g is an antiderivative for f and g of 2 is negative 7, well, basically if I've got g of 2 and I want g of 4, and I don't know very much about g, what I can say is that, all right, well, g of 4 equals g of 2 plus the integral from 2 to 4 of g prime. Okay, so if g is antiderivative for f, then that means that f is the derivative of g, so g prime is going to be f, and I'm going to actually put that in. They told us that g of 2 is negative 7, and so that's why it's going to be, where is it? Answer choice E. Negative 7 plus the integral from 2 to 4 of f of x dx. Or f of t dt, however you feel. Okay. Now this one needs a calculator. Okay. You don't need to be evaluating, values of e to the negative 0.16 t by hand with 19.55 as the rate out. That's just not realistic, right? Now this one, in case anybody's watching this and is concerned that I'm posting secure problems, this kind of was a secure problem and it was slightly different, and I added a little bit of a twist to it, so this is my own problem here. So water's going to be pumped into the tank at the rate R, and then it has a hole in the bottom and it's leaking 19.55 gallons of water per minute. Okay? If the tank started with 800, how much is going to be in the tank after 20 minutes? Well, we know the amount function will be the amount we started with, the 800, plus the integral of rate in minus rate out. So it would be the integral from time 0 to time t of rate in is r, rate out is 19.55, and then we need a dummy variable, so I'll just use like x or something. So I'm going to go over here to the calculator. I'm going to do 800 plus the integral from 0 up to, in our case, 20. So we're interested in where t is 20. Zero to 20 of r of x is 30 times 1 minus e to the negative 0.16 t. Close the parenthesis, subtract the 1955, and integrate with respect to x. And I get 829.143 gallons, and so that's going to be answer choice C. Now we're going to move on to some area volume, and we're getting close to the end of calculus AB now. Okay, I'm going to draw a picture of this region because it didn't come with one. So y equals 5 and y equals x squared plus 1. Those are both graphs that they expect you to be able to just kind of like know what they look like or be able to produce a sketch of them yourself. Okay, that's y equals, that is not y equals x squared plus 1, but I could adjust it so it became y equals x squared plus 1. That'll work. And then y equals 5, that'll be something like this. Okay. So this is the region that we're interested in finding the area of. And what we're going to do is we're going to take a little representative rectangle, and we're going to be adding up top minus bottom. So I'm going to integrate as x runs from, we're going to have to find out these x coordinates right here, but I actually don't think it should be too hard because I'm setting x squared plus 1 equals 5. That's where x squared equals 4. This is negative 2 and 2. So I'm going to integrate from negative 2 to 2 on top minus bottom is 5 on top, x squared plus 1 on bottom. Okay, making sure we're being judicious with those parentheses, right? This is where something bad could happen. I bet they're ready for, basically you integrating 6 minus x squared instead of 4 minus x squared. Okay, but I'm going to simplify first so that I don't make an error unnecessarily. And then this is going to be 4x minus 1/3 x to the third as x runs from negative 2 to 2. It's kind of occurring to me now that I could have been a little bit smarter by just saying it's twice the area from 0 to 2, but I've already gone far enough that I'm just going to kind of stick with this. 4 times 2 is 8 minus 8/3. Minus, when I plug in negative 2, I'll have negative 8 and positive 8/3. Okay. And, all right, so 8 minus negative 8 is going to be 16. And then negative 8/3 minus another 8/3 is going to be negative 16/3. Oh, and if basically this is a whole 16 minus a third of 16, so it's going to end up being 2/3 of 16. That'll be 32/3. Arc length. Okay, so this is not a calculus AB topic, but I always, mix it in with my area volume unit. So this one got in before I switched over to explicitly C topics, but okay, this is fine. If you're an AB student, just go ahead and skip ahead. But the length of the curve, y equals f of x, between x equals a and x equals b. So if it's between x values, then we need to use the y equals f of x arc length formula, which is L equals the integral from x equals a to x equals b, the square root of 1 plus f prime of x squared dx. Okay? So what they're saying here is that f prime of x squared, that's sine squared 2x. So it must be the case that f prime of x is equal to sine of 2x. So really, this is an antiderivative question. We're going to find f of x by taking an antiderivative of sine 2x with respect to x. Okay, an antiderivative for sine is negative cosine. I would leave the inside the same and check for the chain rule. Okay, if I took the derivative of this, I would have positive sine of 2x times 2 for the chain rule, so I need to prepare for that 2 by dividing. So that's where I'd see negative half cosine 2x. Okay. Disk volume. Oh yeah, I like this one. This is the second time I've reminded you of this fact. This was not by accident. Okay, y equals secant x. Okay, suppose you don't know what the graph of y equals secant x looks like. Okay, I think you should be able to see that secant of 0 is positive 1, right? Because it's 1 over cosine of 0. We know that. Okay, just suppose it's, I don't know, like that. And overall, from 0 to pi over 4, it actually doesn't look all that dissimilar from that. But I'm going to just kind of say that's here, and this is y equals secant x. And this is the region that they're talking about. They want to revolve this around the x-axis. So my radius will start at the axis of rotation, and it will reach all the way to the far edge of the region. That will be my radius. Radius is going to be top minus bottom is secant x, and on top, y equals secant x, and on bottom, that's y equals 0. It's the x-axis. So I know that volume is going to be equal to the integral of pi r squared. But since r squared, or since r is secant x, r squared will be secant squared x. Okay. And I know an antiderivative for secant squared x, that's tangent x. It's the second time we've run into that in this video. Okay, 0 to pi over 4. And so this would be pi times the tangent of pi over 4 minus the tangent of 0. And yes, you definitely need to know those values of tangent. Okay, you could compute tangent by doing sine over cosine, or you could draw the triangle, whatever you wanted. And that's just going to be 1 pi. Okay, let's do a washer volume next. So, all right, S is going to be enclosed by y equals 2x and y equals 2x squared. Okay, well, that's 2x, and 2x squared is going to be a parabola. And so I know between x equals 0 and x equals 1, I know that's what it's going to look like. Okay, so you could come in, you could give it a little bit of y-axis, a little bit of x-axis, and then you'd have your region. Okay, this is going to be y equals 2 right there. And, it doesn't have to be perfect. I might draw in my axis y equals 3 up here. It's not drawn to scale, but that's fine. Okay, it doesn't need to be drawn to scale. It just needs to be drawn so that, when I go to get my large radius by reaching from the axis of rotation all the way to the far edge of the region I'm rotating, that's going to be my large radius, and I'll call that A. A will be top minus bottom. On top, I have 3. Bottom, I have the parabola, so that's 2x squared. Okay? Then for my second radius, my smaller radius, I start at the axis of rotation, and I reach to the near edge. Okay? And on the most recent pre-response that we took, I saw a lot of people getting this type of problem wrong, and also not trying to draw a diagram. So, that's what I told y'all. Y'all were really good at drawing the diagrams when we were doing the unit, but somehow y'all forgot along the way, and I need you to remember, just in case the area volume is something you have to do on pre-response. Okay? Which is not super likely for Cal BC, but for AB it's pretty likely. So, and then I need to write down a formula for B. That's going to be top minus bottom. On top I've got y equals 3. On bottom I've got y equals 2x. And so I know that it's, my washer volume is going to be pi times the integral of a squared minus b squared. And it said x needs to run from 0 to 1, so that would be, dx from 0 to 1. Okay, so I think it's going to be 3 minus 2x squared minus, here it is, I found it, it's answer choice A. Okay. Third type of volume we do in this class is cross-section volumes. And remember that for these, volume is equal to the integral of the area formula. In this case, we are going to be taking cross-sections perpendicular to the x-axis, so it'll be dx. Okay. So I am looking for, now drawing the base of this solid might be a little more difficult. So bounded by the y-axis, the graph of arctangent, okay, arctangent, well, arctangent of 0 is 0, and then it increases. Okay, the horizontal line y equals 3. Okay, the limit of arctangent is pi over 2, which is quite a bit less than 3. Okay, and the vertical line x equals 1. Okay. And for a region like this where you're not entirely sure which part they're talking about, keep in mind it needs to be bounded by all four of these things, right? The y-axis, the graph of arctangent, y equals 3, and x equals 1. So the one that's bounded by all four of these curves, or lines, or whatever, is going to be this area that I'm shading in yellow. Okay? Now we're going to take cross-sections perpendicular to the x-axis, so we need to draw one of those cross-sections. And that cross-section is a square, so that's the base of the square. I know that the area of a square is equal to base to the 2 power. And so I'm going to take that area formula and plug it into my integral. Okay, so I'll have, I think I'll be able to do that over here. So it'll be the integral from x equals 0 to x equals 1 of my area formula. So area is base squared. But now I just need to figure out what is the base, actually. Base is going to be top minus bottom. So on top, I've got y equals 3. And on bottom, I've got arctangent x. I've just noticed that this is a calculator problem. So you could have probably, drawn the graph with the calculator to figure out what it all looked like. And yeah, that's kind of unfortunate. So pardon me, I'm going to need the calculator for this. And so my volume is going to be equal to the integral from 0 to 1 of 3 minus arctangent x squared dx, right? It's base squared is the area formula, and I integrate the area formula to get volume. So I can bring in the calculator and integrate from 0 up to 1. 3 minus arctangent x, I'm in radian mode. Okay, close off the parentheses, square it, integrate it. 6.612, there it is. We love integration by parts. We know the formula for it. It's pretty predictable. It works almost the same way every time. And so if you see x times f prime, nothing is the derivative of something else that's also in the integrand, so it's not going to be u to u. It's got to be u to v. Okay? So I'm going to let u be equal to x because I want dv to be something that I can easily anti-differentiate. And while I could easily anti-differentiate x, that would require me to need to take the derivative of f prime. I don't have any information about f double prime in this problem. So I think that dv equals f prime of x is going to be the way to go. I need to take du and regular v. Now, we know that the integral of u dv, or if it's the integral from 2 to 5 of u dv, that's going to be u times v from 2 to 5, minus the integral of v du from 2 to 5, but I'm just not going to have nearly enough room to write that. So we'll put that up here. Okay. And we'll go in and actually do that. This will be equal to u times v, so x f of x from 2 to 5, minus the integral from 2 to 5 of v du. Now they told us that that's 14, right? This thing right here is going to be that 14 here. And this over here on the left, that'll be 2 times f of 2, which is 4, minus 5 times f of 5, which is 7, minus another 14. It looks like a lot of arithmetic. Wait a second. uv minus the integral v du. These are all positive numbers. Oh, well, that would be because I plugged in 2 before 5. That's really embarrassing. Shouldn't have done that. 5 times f of 5 minus 2 times f of 2. That is way better. Okay, so that's 35 minus 14 minus 8. I'll just subtract in a different order. And 35 minus 14 is going to be 21. 21 minus 8 is going to be 13. Yeah, that looks a little better. Okay, partial fraction integration. It's one where if we see that the denominator is factorable, then we're going to want to split it up with the a and the b. Maybe you can see why I chose this one. I chose this one for a very specific reason, so that we can do the algebra and so that we can be reminded of chain rule stuff. So I'm going to say, all right, this integrand, this 7x divided by 2x minus 3 and x plus 2, that's going to be some number divided by 2x minus 3 plus some other number divided by x plus 2. Okay, now I'm going to multiply this equation by both 2x minus 3 and x minus 2, and that will give me 7x equals a times x plus 2 plus b times 2x minus 3. And then I need to take actual values of x that will zero out these things that are multiplying a and b, so like x equals negative 2. That would be negative 14 equals negative 4 minus 3 is negative 7 times b. Well, that means that b is going to equal 2. And if x equals, what would that need to be, 1.5? Yeah, 2x minus 3 needs to equal 0. Yeah, so x equals 1.5. That will give me 7 times 1.5 is 10.5 equals x plus 2 is 3.5a plus 0b. Okay. 3.5 times 3 is 10.5, so a is going to equal 3. Okay. So now I'm integrating 3 divided by 2x minus 3 plus 2 over x plus 2. And I'm just, the whole point of this problem is to remind you that it's not just going to be 3 log of the absolute value of 2x plus 3. That's what you would think. Or 2x minus 3. If I took the derivative of that, I'd end up with 6 divided by 2x minus 3 because of the chain rule, right? 3 over 2x minus 3 times 2 for the chain rule. So I need to prepare for that 2 to come out by dividing there, and that's why it's going to be answer choice A, okay? This is going to be 2 log of the absolute value of x plus 2. We will add a c because it's an antiderivative, even if you can't see it. But the only one that has 3 halves log of 2x minus 3 is going to be answer choice A. So I know it's going to be that one. All right. This next one's an improper integral, okay, because it's got that infinity in the bounds of integration. That's specifically what's making it improper. And if you remember what I told you when I showed you about these, you must transform these into a limit. Now, kind of like L'Hopital's rule, nobody's checking your work. You're not looking at your multiple choice booklet to see, are you showing appropriate work. But if this was free response, I'm going to show you how you would need to present your answer in order to get the credit. Okay, the first thing we need to do, hey, we've got a fraction here. We need to rewrite it so that we can antidifferentiate. This is going to be the integral from 1 to infinity of 6 times x plus 3 to the 3 halves, but the negative 3 halves power because it's in the denominator. So I'm going to antidifferentiate by kind of like adding 1 to the power and dividing by the new power, so that would be multiplying by negative 2 would be negative 12. I'm going to take a second and pause and check my antiderivative to see if it works, right? That would be negative half of negative 12 is 6, x plus 3 to the subtract 1 is negative 3 halves. The derivative of x plus 3 is 1, so I'm feeling good about this antiderivative. Okay. But what I might do when I go to plug in 1 and consider what happens as x goes to infinity, I might rewrite that negative power as a fraction so that I can more easily take this limit, right? Because I'm not going to be abusing infinity notation. I'm not going to just be plugging in infinity in for x. It's not the right thing to do. So I'm going to say that's negative 12 over the square root of x plus 3. That's what the negative half power is. And I'm going to take the limit of this as x goes to infinity. And then I'm going to subtract what happens when I plug in 1 for x. Well, that would be the square root of 4. Okay, so as x approaches infinity, this fraction that I'm highlighting in yellow here, or this limit, it's going to go to 0 because the numerator is going to stay the same, the denominator is just going to get bigger and bigger. So I've got 0 minus negative 6, because, negative 12 divided by 2. And so 0 minus negative 6 is going to be positive 6. All right, here's a couple of, miscellaneous, obscure integration topics that, could come up. I'd say, and completing the square, that's one of the most forgotten about topics in all of AP Calculus, because it has to be just right, or else the algebra is really intensive. Okay, this looks like a typo, right? 1 over x squared plus 2x plus 2. You look at it and it's like, oh, I think I can factor this. I should be able to factor it. But, that 2 in the middle, I feel like they meant to hit the 3 button, right? It looks like a typo. It's not quite right. No, it's arctangent. Okay, so remember the derivative of arctangent is 1 over 1 plus x squared. So the derivative of arctangent of x plus 1 would be 1 over 1 plus x plus 1 squared. And that's going to be 1 over x squared plus 2x plus 1 plus an additional 1, and that's the integrand. Okay, so I'm just reminding you that that can happen when it looks a little off. We couldn't factor that, so we couldn't do partial fractions. With long division, if we are confronted with a fraction and we see that it's bigger on top, we're going to do long division. But in our class, long division pretty much just means synthetic division. So we're going to copy down the coefficients, 6x to the 2, negative 4x to the 1, negative 25, and then we're going to process the 0 of the denominator. So we're going to run 6 through there. We're going to multiply, add, multiply, add. Okay. So the quotient is going to be, if I'm dividing 6x squared by x, it's going to start off with 6x plus 8 minus 9 divided by the divisor, which is x minus 2. And that's what I'm integrating, and that will be much easier now, right? The antiderivative of 6x is 3x squared. Antiderivative for 8 is 8x. And then the next one will be negative 9 log of the absolute value of x minus 2 plus c. So that's why it's going to be answer choice A. Okay, now we're going to move on to parametric curves. Here we've got x of t and y of t, and we want the equation for the line tangent to the curve. And while I'm at it, I'm going to add another problem to this because I just realized I didn't do the other arc length formula. That was a huge mistake. I knew I was going to forget something, but well, if that's the only thing I've forgotten so far, then I'm probably doing good. If there's anything else I've forgotten, hopefully you'll let me know, and I'll just add that problem on for next year, and I guess I'll re-record this. But okay, we want the equation of the tangent line. Well, we need the slope. So dy dx for a parametric set of equations is going to be y prime divided by x prime. Now we need to find the time when the thing's at 3 and 8. I'm going to take the easier looking equation, that's y equals t cubed, and set it equal to 8. So t to the 3 equals 8, that means t equals 2, and dy dx at t equals 2 is equal to 3 times 4 is 12, divided by 4 minus 4, that is 12 divided by 0. That doesn't exist. Okay, so if dy dx fails to exist because of division by 0, I know I've got a vertical tangent line. So at the point negative 3 and 8, I've got a tangent line. That's the picture of my tangent line. That's going to be the set of all points that have that x coordinate negative 3, and that's why the answer choice is going to be A. Okay, then I'll just kind of add my own question here. What's the length of curve C from t equals 0 to t equals 2? And if they ask you about a length for t values, you're going to use the parametric formula, and that would be the integral from t equals 0 to t equals 2 of the square root of not 1 plus dy dx squared, but dx dt squared plus dy dt squared. Now, in general, this is going to either be a calculator question or which of these is the right integral, and so I'm just going to show you how to write the integral, and that'll be good enough. All right, second derivative of y with respect to x on a parametric curve. For my money, this is the most obscure formula in AP calculus. Okay, we do it the once. It's not really something we need to use a whole lot. It is something you need to remember, though. So what we're going to do to find this derivative, second derivative of y with respect to x, we're going to take the derivative of dy dx, and we're going to divide by dx dt. Yeah, that's pretty ugly, but I really didn't leave myself enough room. So I'm going to find dy dx. So dy dx is y prime divided by x prime. Okay, so now I need to take the derivative of dy dx. So dy dx prime, that's going to involve quotient rule. Bottom times the derivative of the top minus the top, and maybe I'll call that 2t plus 2, times the derivative of the bottom divided by the bottom squared. Hold on. We call that e to the 2t if you wanted. And then we need to divide by dx dt. So that would be like throwing in that e to the t in the denominator. Okay. And so I think we're just going to plug in t equals 1 now, and we're going to get e times 2 minus, when t equals 1, I'll have 4 times e to the 1 divided by e to the 1 squared times e to the first. So it's a total of 3 powers of e, but I guess I could factor out the e's up here. 2 minus 4, cancel with that one, and that would be negative 2 divided by 2 powers of e. That was an interesting one. Negative 2 divided by e squared. Okay, that was a good one. I like it. Okay, we need to be able to take the slope of a polar curve. And so we need to remember that dy dx is equal to y prime of theta divided by x prime of theta, where y is equal to r sine theta. Okay, so I'm going to take that derivative using the product rule. Take the derivative of 3 theta, leave sine theta the same, then leave 3 theta the same, and take the derivative of sine theta. Okay. Plug in pi over 2. I know sine of pi over 2 is 1, and cosine of pi over 2 is 0. Okay, so it's going to be 3. And then x prime, or x is our cosine theta. X prime, I'm going to use the product rule. And because the derivative of cosine is negative sine, I'll have negative 3 theta sine theta. And I can plug in for x prime at pi over 2, and that will give me 3 times the cosine of pi over 2 minus 3 times pi over 2 times the sine, which was 1. Okay, so dy dx is going to equal 3 divided by negative 3 pi over 2. Okay. So that 2 would get kicked back up to the numerator, and 6 divided by negative 3 is going to be negative 2 divided by pi. Okay. With polar area, most of the battle is you need to remember the formula, right? So we remember that area for a polar situation is the integral of 1/2 r squared d theta. At this point in the year, when you're about to take the exam, you do not need to be concerning yourself with y, although if you are interested, you can go back and watch the video and see why. It just has to do with the geometry of circles. And we're going to integrate that between 2 theta values, right? For now, we're just interested in being able to fluently solve these problems. And this is going to be 1/2 of the integral. Okay, we're starting here at theta equals 0. We're going to end over here at theta equals pi. R is theta, r squared d theta. So this is one that we can actually do by hand. Usually R depends on like sine or cosine. It's got some trig in it, and we would have to square that, and we don't anti-differentiate sine squared theta and cosine squared theta with respect to theta in AP calculus. So we don't really have to worry about that, doing it by hand. But this is one that you could do by hand. So that would be 1/2 of antiderivative for theta squared with respect to theta would be 1/3 theta to the third, and we let theta run from 0 up to pi. So that would be 1/2 times 1, I'll factor out the 1/3. That would be pi to the 3 minus 0 to the 3. So I got pi to the 3 over 6. And there it is. All right, now I see here where this might be a situation where I've got like two polar curves going on. The test is always start at the origin, reach out to the far side of the region you want to find the area of, and oh look, I hit two different curves, so I need to subtract two different areas. If you're only hitting one curve at a time, you're only integrating on one of them. Okay. Now, I'm going to be, so I'm going to do outside minus inside. So it's 1/2 of the integral of, it looks like from pi to 2 pi. And on the outside, I've got 1 minus sine theta. Plus, pardon me, minus, I'm subtracting because I've got this circle area that I need to subtract. 1/2 integral from pi to 2 pi on that. Oh, that's 1 squared d theta. And they're going to combine these. Okay. And there it is. 1/2 2 pi, 1 minus sine theta squared minus 1 squared. Yeah, there it is. All right. Which of these series converges to 2? All right. Well, I know that this one doesn't converge. This diverges by the divergence test because the terms don't even go to 0, so it doesn't really have a chance to converge. Right? Diverges by the nth term test because the limit of the terms is non-zero. The limit of the terms is 2, and that's great, but 2 plus 2 plus 2 plus 2 plus 2 forever does not add up to 2. Okay? Here we have ourselves a geometric series. And I feel like they might want you to think that the ratio is 8/3, but the ratio is the number that's getting taken to the nth power. So this is geometric with common ratio -1/3 to the, or -1/3, right? Since the absolute value of the ratio is less than 1, it converges, and so I need to check using the formula for the sum. In this case, the total would be first term, which is where n equals 1, so 8/3. Multiplied by 1 over 1 minus r. So 1 over 1 minus -1/3. Need to do some arithmetic here. 8/3 multiplied by, well, that'd be 4/3. So if I have 1 over 4/3, that's multiplying by 3/4. And that is 8 divided by 4, which is 2. Okay, so I know that 2 works, so I got that one out. Oh, and this one's also out because 1 is definitely diverging. And 1/2 to the n, okay, this is geometric, r is a half. Total is going to be first term, which is where n equals 0. It's 1. Times 1 over 1 minus that ratio. Okay, 1 minus a half is a half. 1 divided by a half is 2. That's going to be 2 and 3 are both converging to 2. And what are all values of p for which this thing converges? So this is kind of getting at the idea of the limit comparison test as we use it a lot in AP calculus. On top, I've got n to the 1/2, and on bottom, I've got n to the p plus 1. We know that these series, the terms need to be bigger on bottom by more than 1 power. Okay, so I need p, the difference in p and a half, to be bigger than 1. That's how much bigger we are on bottom is the difference between p and a half. So I'm going to add 1/2 to both sides, and I know that p is going to need to be greater than 3/2. Right. Now we got the integral test. If the integral from 1 to infinity of 1 over x squared plus 1 dx is pi over 4, okay, that means that the corresponding series converges, right? Because the integral converges. They're either both finite or they're both infinite. And another thing we need to know is that the series is bigger. I think that's worth just knowing. The series is bigger. So I know that this one must be false. Okay, this one must be true, and this one actually is going to be false because the series is bigger, so it can't be equal. So this one's false as well. Okay. So must be true is 2 only. Okay. If you need to know why the series is bigger, then you need to go back and watch the video test and look for the proof of the integral test on my channel, something like that, and you'll see why. But the big takeaway from the integral test is if the integral exists, then the series exists. If the series exists, then the integral exists, and the other way too. You know, if one diverges, then the other will also diverge. All right. Alternating series. I decided not to go into absolute and conditional convergence in this video. I've got one problem that talks a little bit about it on an interval of convergence for a power series. You know, if you need more on that stuff, go back in and look at the lessons from throughout the year. Yeah, this video is really kind of focused on the fundamentals. None of these are going to be the hardest question on the exam. I was really just going for each topic once at a kind of medium level. So as for alternating series, we need to think about the alternating series test, which is that if you've got a series that's got terms that are alternating, decreasing in magnitude, and having a limit of 0, then you know that series converges. Okay? That's what the alternating series test is good for. It's good for showing that an alternating series converges. Okay? If the limit of the terms is not 0, well, you don't need to use the alternating series test. That's the nth term test for divergence. So we don't really use the alternating series test to show that a series diverges. Okay, so what this kind of boils down to is that it needs to be alternating and having like a fraction where it's bigger on bottom. That's what's going to cause something to decrease in magnitude and go to 0, outside of like a negative exponent, which would of course be the same as being larger in the denominator. Okay, this one, square root of n, is not as big as n, so I know that these terms, or you could say that I could cancel off stuff, and this would be square root of n in the denominator, and we know that's one that's going to converge conditionally. Because it wouldn't converge if I took away the alternating part. Okay, so yes, this one converges. Negative 1 to n over log n. Okay, this one could go either way. I stole this one from like a review book or something. That one should say n equals 2. Okay, if it says n equals 2, then that one's going to converge using the alternating series test. N equals 1, you've got log of 1 in your denominator of your first term, so that's going to be troublesome for you. But I'll say that this one now, since log of n increases as n increases, and it can get as big as you want, well, this is going to have the same thing going on. It's going to be alternating. The terms are going to get smaller because the denominator gets bigger, and, well, the limit of the terms is 0. Okay, number 3, this one is, okay, when n equals 1, that's cosine of pi, so it's negative 1 plus 1 minus 1 plus 1 minus 1, so on. And that doesn't converge to anything, so we say it diverges. Okay. If you think about the totals is bouncing back and forth from negative 1 to 0. And so I've got 1 and 2 only. All right, ratio test. I think I might have put this one on the unit test. I like this one a lot. If we apply the ratio test to the series, which is considering the limit as n approaches infinity of the n plus first term, so we plug in n plus 1 where we see n, divided by the nth term. So that's multiplying by the reciprocal of the original terms. So e to the n. Okay, I'm going to rewrite e to the n plus 1 as e to the n times e to the 1. Wait a second, I didn't actually plug in n plus 1 for n there. Oh, that's a shame. Okay, but then I might, kind of rearrange like I like to do with the ratio test, and put n factorial over here and n plus 1 factorial, which I could write as n plus 1 times n factorial down there. And now I'm going to start canceling stuff off, e to the n factorial, and this is the absolute value of e divided by n plus 1 as n goes to infinity. Okay, that's going to be less than 1, showing the series converges absolutely. Yeah, I mean, this is an old problem. Now we know that if the ratio test comes back less than 1, not only is the series converging, it's converging absolutely. All right, with interval of convergence, I find that pretty often they ask these questions that kind of get at the idea of, okay, you've got yourself a power series, this one's centered at 1. They're going to give you some information about the radius and, and then ask you about what could be true, must be true, might be true, something like that. If it converges conditionally at x equals 5, then we know that x equals 5 is an endpoint of the interval of convergence, because we compute the interval using the ratio test, and we know if the ratio test comes back less than 1, then that's where the series is absolutely convergent. So that's going to be on the interior of the interval, because these endpoints are where that ratio test comes back exactly 1. So if I go 4 that way, then I need to be able to go 4 that way. And I will know that, since that's an endpoint, anything out here diverges, and anything in here converges absolutely. Okay, from there to, well, in this case, I know it's there, but I don't know what's happening at -3. It could go either way. It could converge absolutely, it could converge conditionally, it could diverge at that endpoint. So we don't really know anything about it at -3, but at -4, I know that's outside of the interval of convergence, so it's definitely diverging with certainty. Because I know that the radius of convergence is exactly 4. Because if a power series is going to be converging conditionally, it's because it's converging conditionally at the endpoint of its interval of convergence. All right, so our known Maclaurin series, we need to be able to work with those. So we know the Maclaurin series for e to the x starts with 1 and x squared over 2 factorial and x to the 3 over 3 factorial. I gotta think that's going to be enough terms for our purposes here. F is e to the 2x, so I replace x with 2x wherever I see it in the formula for the Maclaurin series. And I need to be careful about parentheses because that will cause you big problems. And take the derivative, and now you could probably do 2e to the 2x, and that would work out fine for you, but if it wasn't such an easy derivative to take, you would want to take the derivative term by term, and so that's what I'm going to do. Actually, I'm going to rewrite f by doing some simplification. 1 plus 2x plus 4x squared over 2 factorial is 2x squared. 2x cubed, or taking 2x and cubing it, that gives you 8x to the 3 divided by 3 factorial is 8 divided by 6 is 4/3 x to the 3rd, and so on. And I'm hoping that I can just, match up the first few terms to the answer choices. F prime is going to be equal to the derivative of 1 is 0, derivative of 2x is 2, 4x squared. 2 plus 4x plus, oh, they actually did this. That's interesting. Okay, whatever. Sure. That's going to be my answer choice. Okay. Now we're going to cook up our own Taylor series for a function that we don't really know much about besides, we got a table of values or something. And so we know that the third degree Taylor polynomial is going to be, centered at x equals 1 is f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1, second derivative, second factorial, second power of x minus 1. And then because it's third degree, I need to go up to x to the 3. So I'm still taking the derivative at 1, dividing by that same factorial number, and having that same number of powers of x minus 1. Okay. Now I'm interested in just plugging in these numbers. 2 minus 3 times x minus 1. F double prime divided by 2 factorial is 4 divided by 2, x minus 1 squared. That might be enough to eliminate, right? 2 minus 3 times x minus 1. Oh, that didn't do much for us at all. Oh, actually, no, this is. Okay, so first few, x plus 1. No, get that out of here. We don't have any interest in that. Okay, that would be if it was centered at -1. And now, since it's 4 divided by 2 times x minus 1 squared, yeah, that will be answer choice A. Okay, connecting a Taylor polynomial to derivatives. Okay, this is a good skill to have. So we know that the fourth derivative information comes from the fourth power term. And I need that plus as well because that matters, right? So it's positive 2 divided by 9 times x to the 4. Well, I know that the fourth power term in a Taylor series for f centered at x equals 0 is going to be f's fourth derivative at 0 divided by 4 factorial times x to the 4. So looking at the coefficients, this 2/9 is f's fourth derivative divided by 4 factorial, meaning that f's fourth derivative at 0 is going to be 2/9 times 4 factorial. Well, 4 factorial is 4 times 3 times 2 is 24. I think that's 48 over 9. Oh, wait, no. 24 has a factor of 3 in it, so that's 8 divided by 3, and that's 16 over thirds. There we go. Just 4 more left. So the Lagrange error bound. Function f has derivatives of all orders for all real numbers. They give us a maximum value of f's fourth derivative and f's fifth derivative's absolute value. Okay, so we're going to use a fourth-degree Taylor polynomial around x equals 0 to approximate f of 2, basically. And so this absolute value over here, this is talking about the error in my approximation. But we know that the Lagrange error bound says that error, if we used a fourth-degree polynomial, is going to be less than or equal to the maximum of the absolute value of f's fifth derivative divided by 5 factorial multiplied by the absolute value of the difference between the center or the approximation x value that we plugged in 2 to approximate f of 2 minus the centering value, it's about x equals 0, to the fifth power. So the maximum value of f's fifth is 3/2. So it's 3/2 times 1 over 5 factorial times 2 to the fifth. Okay. And so 2 to the fifth is, what is, okay, 3/2 times 2 to the 5 over 5 factorial times 3/2. Oh, yeah, okay, pardon me. I can't believe that I was not seeing that, but yeah, that's going to be our answer. Okay, so my thing about the Lagrange error bound is provided you just know the formula and know how it works, these are not hard questions because they always give you the information you need. So you just plug in the pieces, get your right answer, move on. All right, now, if you know me, you know I'm not going to bring up the Lagrange error bound without contrasting it against the alternating series error bound, which is easier. It's just the next term. Okay, so we're using the first 3 terms, so that's n equals 1, n equals 2, n equals 3. So my error is no more for an alternating series than the absolute value of the n equals 4 term. Yeah, be a little careful if they said you're going to use 3 terms and n start at 0 or something. But in this case, we're starting at 1, so it's going to be the absolute value of the n equals 4 term. So I can just say, all right, -1 to the 3. Sure. We're taking the absolute value, so it's not going to matter. 4 squared plus 3 is 16, and 3 is 19. The absolute value of -1/19, that's 1/19. We can do this. Euler's method. That's something that we did recently, and it seems like we're pretty good at. So we know that if we're going to use a step size of 0.5 starting at x equals 1, trying to get to x equals 2, it's going to be 2 steps, 0.5. It's going to be 1.5. So my first step, I'll go 1 to 1.5, and then my second step, I'll go 1.5 to 2. Okay, so my first tangent line, I'm going to need a point. That'll be 1, -3. I'll need a slope. Y prime equals 2x plus y. So I'll have an equation y minus -3 equals the slope times x minus +1. Okay, I'll take my first step, and that's where x becomes 1.5. And then y will equal -3 minus 1.5 minus 1. So that's -3.5. Okay, so that's my new point that I can start for that I can use to start my second tangent line, 1.5 and -3.5. My slope is y prime equals 2x plus y. So my second equation would be y minus negative 3.5 equals the slope times x minus my x coordinate is now 1.5. I'll take my second step. That will be x equals 2. And then y will equal negative 3.5 minus half. I did not realize I was off my shot, pardon me. Minus half of when x is 2, that's 2 minus 1.5, 0.5. All right, so 3.5 minus a quarter is negative 375. Okay, and then I always point this out, but if you're always using the same step size and it's always 0.5, then that number that you're multiplying the slope by needs to consistently be 0.5. And if it's not, then you've probably made an error along the way. And the last problem I got for you is about logistic differential equation. So you read the word logistic in Cal BC, and you just need to activate all those trivia facts, right? And maybe I can list them off for you. You need to know the form of the differential equation, and in this case, we're going to factor out a 1 over 850. So that's going to be n divided by 8,500 with the 10 and the 850 multiplied by 850 minus n. Okay. Unless you're just like, oh, I know that means the carrying capacity is 850. If you see it in the denominator right here, that's good for you. Okay. If you don't, you need to know, okay, 850, that's my carrying capacity. That's the limit as t approaches infinity of the population. Okay. So this one is definitely true because of the form of the differential equation. We also need to know about the shape of the graph. Okay, now if n of 0 is 105, which is less than half of the carrying capacity, okay, that means that if this is, let's just say this is 850, if we're starting at 150, it's going to have that S-shaped curve. That's something we need to know. And so that will be, and then the point of inflection, the special trivia at 425, that's where the maximum growth rate is happening, and there's a point of inflection there. It's also, where it's going from concave up to concave down. So this must be true, because the second derivative is going to exist and be continuous, with that first derivative given there. And then, okay, I'm kind of running out of color, but up here, when n is greater than 425, okay, n is increasing. That means the derivative of n is positive, and the graph of n is concave down, which means the second derivative of n with respect to t both times would be 0, and so this one's also going to be true. Wait, which of these statements is false? Hold on. Oh, yeah. dn dt has a maximum value when n is 105. No, it needs to be 425. And since this one's false, that's going to be the one I'm going to choose. Okay. This has been a marathon. An hour and 48 minutes. Kind of all in one go. It's a lot for me. Hopefully you split this up into maybe 2 sittings or something. But, if you're practicing with doing some last-minute practice before the AP exam, I hope this was helpful. This was a long problem set, but it was a long year. We learned a lot. And if you're in my class, I really enjoyed it. I enjoyed working with you. And I really appreciate you watching those videos, and I hope they helped. But, the only, really last-second advice I have for the AP exam, control the things you can control. Know your formulas. Don't stay up all night studying. Get your rest. And don't show up on an empty stomach. Eat something before you show up. And those are 3 things that you can do that will just set you up for a little more success. Thanks for watching.